You are sitting in a room that appears ordinary. The walls contain the same familiar objects you have seen countless times. The air has weight, and light falls through it in straight lines. You assume that the passage of time here is uniform, that events outside your perception obey rules that are continuous, predictable, and stable. Yet, in the vastness beyond your room, beyond the gravitational pull of your planet, there exist events that dwarf comprehension. Explosions that release more energy in a single instant than the sun will emit over its entire 10 billion year lifetime. Phenomena whose brightness can outshine entire galaxies, yet they are fleeting, ephemeral, and precisely measured. These are not myths, nor distant conjectures. They are observed, quantified, and catalogued by instruments that trace photons and gravitational ripples. The contradiction is immediate and undeniable. Space, which you conceive as largely empty and passive, occasionally produces manifestations of raw energy that challenge your intuition about causality, scale, and the continuity of time itself. Every detection carries an implication. The universe is capable of extremes that our senses and everyday experiences cannot anticipate. This video will trace those extremes, not through narrative flourish, but through observation. You will confront the most powerful events ever recorded in space and the consequences that arise when measurement collides with expectation. The question is not what could happen, but what is already happening that defies the assumptions you carry about reality. The quiet before the flash. You imagine that most of space is still. Stars burn steadily, planets orbit predictably, and interstellar gas drifts silently. Yet telescopes detect regions that appear inert, where energy accumulates in silence for millions of years, only to erupt with a force that temporarily reshapes surrounding space. Observation shows that this stillness is deceptive. Even apparent calm can harbor the seeds of violent transformation. When you look at these regions through the lens of different instruments, the apparent emptiness begins to dissolve. X-ray observatories reveal diffuse clouds of superheated gas, moving imperceptibly, stretching and compressing under gravitational influence. Radio surveys detect faint oscillations in plasma that trace the slow migration of magnetic fields. In isolation, these movements are subtle, almost imperceptible. Yet taken together, they indicate energy is stored on scales far larger than you would intuitively expect. The accumulation is not chaotic. It follows measurable patterns dictated by mass, gravity, and the interplay of electromagnetic forces. What appears passive is, in fact, highly organized. Your expectation is that space is largely uneventful, but observations indicate that energy can gather silently in ways that are incompatible with a naive understanding of stability. Interstellar clouds, for example, gradually condense under their own gravity. Over millions of years, density increases, magnetic fields intensify, and internal pressures rise. These processes occur without producing detectable heat or radiation that would signal imminent change. Instruments record only a slow, almost imperceptible shifting of matter. Yet the cumulative effect is dramatic. When the threshold is reached, a sudden release occurs, a supernova, a gamma ray burst, or a jet of relativistic particles, transforming the surrounding environment almost instantaneously. Even the vacuum between stars is not empty in the way you might assume. Observations of intergalactic space show faint ripples in the cosmic microwave background, variations in particle density, and pervasive magnetic fields threading across millions of light years. These structures are subtle, often below the threshold of immediate perception, yet they can channel, store, or redirect energy over extraordinary distances. What seems to be stillness is instead a latent tension, a quiet pressure that has measurable consequences once released. You might think that these events occur in isolation, disconnected from the rest of the universe, but measurement reveals connectivity. Shockwaves from supernovae compress nearby gas clouds, triggering further collapse and star formation. High-energy photons ionize surrounding regions, subtly altering chemistry on scales of light years. Even gravitational waves from distant collapses pass through ostensibly empty regions, imparting imperceptible distortions that accumulate over time. Observation confirms that the calm of space is never truly inert. It is a stage on which extreme events are preconditioned long before they appear. The quiet accumulation of energy also forces reconsideration of temporal scale. From your perspective on Earth, millions of years may appear vast, yet in the lifespan of stars, such periods are brief. Observing the precursors to violent events challenges your assumptions about causality. Slow processes can lead to outcomes that are sudden, localized, and extreme. Measurement bridges these scales, connecting imperceptible, protracted change with instantaneous cosmic transformation. Ultimately, the quiet before the flash is both observable and unnerving. It demonstrates that stability is often a veneer, that latent power pervades space in measurable, structured ways, and that the universe does not conform to your expectations of predictability. What you perceive as calm contains within it the inevitability of eruption, encoded in energy distributions, gravitational interactions, and the architecture of matter itself. Observation leaves no doubt that the cosmos, even in its most tranquil regions, is preparing for events whose magnitude surpasses ordinary comprehension. The stillness you assume to be passive is instead active, deliberate in its accumulation, and fundamentally indifferent to your perception. Gamma-ray bursts, light that breaks time. You expect light to travel predictably, illuminating the universe evenly over vast distances. Gamma-ray bursts, the brightest explosions ever observed, violate that expectation. In seconds, they release more energy than the sun emits in its entire life. Measurements of their light curves reveal structures that are internally coherent, yet inconsistent with any process you would consider stable. These bursts are detected as sudden, intense flashes in the gamma-ray spectrum, often lasting from milliseconds to a few minutes. Their brevity is misleading. The energy involved is concentrated to such a degree that, if it were applied locally, it would obliterate planetary systems within parsecs. Yet they occur billions of light years away, and even at that distance, the photons that reach your instruments are sufficient to reveal the geometry, timing, and intensity of the explosion with remarkable precision. Observation confirms that these are not random events, nor phenomena of diffuse emission. They are sharply defined, highly structured, and entirely extreme. When you examine the light curves, a pattern emerges that seems paradoxical. The intensity rises and falls with precision, producing sub-millisecond variations within a process that releases energy comparable to the output of an entire galaxy. The internal coherence implies a mechanism that organizes energy release across scales you cannot directly observe. Yet the total output contradicts every stable or incremental model you might propose. The energy density is far beyond the capacity of known stellar processes to release gradually. What your instruments measure is both structured and instantaneous, a collision between predictability and chaos. These bursts are categorized into short and long durations, each associated with a different astrophysical origin. Short bursts are typically linked to the merger of compact objects, such as neutron stars. Long bursts often result from the collapse of massive stars into black holes. In either case, the observation is striking. The mechanisms that release the energy do so without warning, and the spatial concentration is extreme. Jets of gamma rays are emitted along narrow paths, often a fraction of a degree wide, and yet they travel across billions of light years with minimal dispersion. Observation shows that the universe can accelerate energy to near light speeds, then focus it with extraordinary precision. You might assume that light behaves uniformly across space. Gamma-ray bursts challenge that assumption. Their photons arrive in sequences that encode the history of the source event, yet their propagation is influenced subtly by the curvature of spacetime, the interstellar medium, and cosmic expansion. Measurement reveals tiny delays and frequency shifts, which, when analyzed, indicate the interaction of extreme energy with the intervening universe. Even light, which you consider a constant, carries anomalies that are directly measurable. The consequences of these events extend beyond raw luminosity. Gamma-ray bursts trigger shockwaves, ionize interstellar gas, and generate afterglows detectable across the electromagnetic spectrum. Observation confirms that these are not isolated phenomena. They interact with their environment, transferring energy across spatial and temporal scales. Their transience contrasts with the persistence of their influence. Regions of space that appear unaffected immediately afterward carry signatures of these events for thousands or millions of years. Ultimately, gamma-ray bursts reveal a universe in which energy is concentrated, released, and propagated in ways that defy intuitive expectation. Observation demonstrates that stability is not the default condition. Even the most fundamental constants, light speed, energy conservation, spacetime geometry, play out within contexts of extreme and structured violence. You are left with a subtle unease. The most basic phenomena you take for granted, such as light moving across space, can manifest in forms that are precise, coherent, and yet entirely incompatible with ordinary assumptions about continuity, scale, and temporal progression. Gamma-ray bursts do not bend the rules of physics. They reveal their limits, demonstrating that measurement alone can uncover processes that are both extreme and orderly, transient and persistent, simple in principle, yet overwhelming in effect. Observation leaves no room for doubt. The universe produces events so powerful that they redefine what it means for light and time itself to be predictable. The collapsing giant stars are thought to die quietly, shedding layers over millennia. Some, however, end in a collapse so complete that the core vanishes into a singularity, warping space-time. You can measure the collapse indirectly through gravitational waves and high-energy photons, but the speed and scale of the collapse defy simple causality. Matter and energy vanish in a way that challenges your conventional sense of continuity. In most massive stars, the balance between pressure from nuclear fusion and gravitational pull maintains stability for millions of years. When fusion ceases, gravity accelerates the inward collapse. In typical stars, this leads to a supernova, which is already extreme in energy and duration. But for the most massive stars, the collapse progresses beyond the limits of ordinary physics. Observational data, primarily from gamma-ray detection, X-ray satellites, and gravitational wave observatories, show that the core contracts to a region so dense that conventional spacetime itself is distorted. Measurement confirms that this is not gradual. The transition from dense core to singularity occurs in fractions of a second, producing shockwaves and photon emissions that traverse surrounding space almost instantaneously. You might assume that mass and energy remain locally conserved during such events, yet observations challenge that notion. Gravitational wave signatures from these collapses reveal that energy is radiated in forms that do not correspond to the visible ejection of matter. Instead, a significant fraction of the star's mass disappears from the observable universe, concentrated into the singularity. Photons and neutrinos provide only partial records of the event, leaving an incomplete but precise account of the energy dynamics. The observable consequences are coherent and measurable, yet they suggest a continuity of matter that is fundamentally altered. The implications for spacetime are profound. The gravitational field of a collapsing giant increases exponentially as the core contracts. Light passing near the core is deflected, stretched, and redshifted in ways that can be measured from millions of light years away. Instruments capture these distortions with increasing precision, revealing a local geometry that bends all known rules. Observation shows that a region of space can be radically transformed within seconds, compressing energy and curvature in ways that are extreme yet entirely predictable through general relativity. Collapse is not always symmetric. Data from asymmetrical supernovae and black hole formation indicate that jets of material and energy can be ejected along particular axes, while other regions vanish into the singularity. Observation demonstrates that the distribution of expelled matter is highly structured, even in the context of extreme chaos. This structure allows astrophysicists to reconstruct the event from distant signals, yet the underlying mechanism remains almost counterintuitive. A star collapses, yet the information about the collapse persists in measurable traces across light years. Time itself is implicated. The core's collapse occurs on a scale almost instantaneous to your perception, yet the propagation of energy outward unfolds over minutes or hours, depending on distance. Light, reaching your instruments, carries timestamps that encode the event's internal sequence. Observation forces recognition that the universe can operate simultaneously at multiple temporal scales. A singularity forms in milliseconds, while surrounding matter reacts over years. Measurement makes clear that extreme density and energy introduce temporal discontinuities relative to external observers, even though all processes obey physical laws locally. Ultimately, the collapsing giants demonstrate that the universe can concentrate matter and energy into extremes beyond ordinary intuition, warping space-time, producing measurable gravitational waves, and generating high-energy emissions that ripple across cosmic distances. Observation confirms that these events are real, precise, and internally consistent. Yet the scale and speed of the collapse undermine your expectations of continuity, gradual change, and causality. The universe is capable of sudden, extreme transformation, even in systems as familiar as stars, and you are confronted with the persistent reality that mass, energy, and space-time are far less intuitive than your daily experience would suggest. Supernovae, the recycling of the cosmos. Explosions of massive stars are familiar in concept, yet observations reveal that no two supernovae are identical. The energy distribution, the spectrum of emitted particles, and the formation of neutron stars or black holes introduce anomalies. They are violent yet patterned, suggesting that the universe balances predictability with extremity in ways that your intuition cannot reconcile. Supernovae occur when a star exhausts its nuclear fuel and can no longer resist gravitational collapse. From your perspective, this process may seem inevitable and uniform, a simple end to stellar life. Measurement, however, exposes a complexity that defies this assumption. The luminosity of supernovae varies across events. the emission of neutrinos fluctuates in ways that reveal asymmetries in the collapsing core, and the ejected material is structured into filaments, knots, and shock fronts, rather than being dispersed uniformly. Observation confirms that each explosion carries a unique signature, determined by the interplay of initial mass, rotation, magnetic fields, and surrounding medium. Predictability exists only in broad terms. The details remain extreme and variable. You might assume that energy released in a supernova dissipates uniformly across space, yet observation shows otherwise. Shockwaves propagate unevenly, compressing some interstellar clouds while leaving others nearly untouched. High-energy photons travel in specific directions, illuminating regions at different times and scales. Radioactive isotopes, forged in the explosion, seed nearby gas clouds and trigger chemical processes that persist for millions of years. Measurement reveals a dynamic choreography. Matter is destroyed, remade, and redirected in patterns that are measurable yet cannot be fully anticipated. The universe recycles its components with a precision that feels deliberate, but arises entirely from natural processes. The remnants of supernovae further illustrate this tension between chaos and order. Neutron stars emerge with predictable mass ranges, yet their rotation rates, magnetic field strengths, and emission of radiation vary dramatically. Black holes form in some cases, introducing regions where space-time is dramatically warped and direct observation is impossible. Observation reveals that these remnants encode information about the progenitor star and the explosion itself, but not in ways that simplify understanding. Instead, the data challenge assumptions. The past of the star can be reconstructed, yet never perfectly, leaving gaps that are precise, measurable, and fundamentally unsettling. Time is implicated in multiple ways. The initial collapse occurs over seconds, but the expansion of the supernova remnant continues for tens of thousands of years. Light from distant supernovae reaches Earth with delays of millions or billions of years, preserving a record of cosmic history. Measurement allows you to probe these timescales simultaneously, connecting the briefest moment of collapse with the protracted influence of the explosion on surrounding space. Supernovae therefore operate across scales that your perception of time cannot easily accommodate, revealing temporal structures that are measurable yet counterintuitive. Chemical enrichment is another consequence. Elements heavier than iron are forged during the explosion and dispersed into space, eventually forming new stars, planets, and ultimately the material of life. Observation shows that these processes are neither uniform nor random. They are structured, patterned, and measurable in their distribution across galaxies. Yet the formation of each element and its journey from one star to the next remains unpredictable in detail. The universe demonstrates order and extremity simultaneously, recycling matter with precision while retaining inherent uncertainty. Ultimately, supernovae illustrate the paradoxical nature of cosmic events. They are violent, transformative, and extreme, yet governed by physical laws that allow measurement, prediction, and reconstruction. Observation reveals a universe in which destruction and creation are inseparable. Energy and matter follow deterministic principles while producing unpredictable outcomes, and even the most catastrophic events carry structure, balance, and measurable consequence. These explosions are the mechanism through which the cosmos organizes itself, yet they continually defy intuition, leaving you with the unsettling awareness that the universe is far more extreme and methodical than your ordinary experience would suggest. Magnetars, stars with magnetic madness. you might assume magnetism on a cosmic scale to be diffuse and weak. Magnetars contradict this assumption, concentrating fields so intense they alter atomic structures and generate bursts of gamma rays detectable across galaxies. Observation confirms that these fields exist without apparent cause, defying the gradualist logic that governs terrestrial magnetism. Magnetars are a type of neutron star, the collapsed remnants of massive stars that have already passed through supernova. Their magnetic fields are extraordinary, measured at 1,000 trillion times stronger than Earth's. From your perspective, this intensity is almost inconceivable. Instruments detect the effects of these fields directly. Atoms are distorted, energy is trapped, and the surrounding space is warped. Photons emitted from the magnetar are polarized in alignment with these extreme fields, allowing astronomers to reconstruct their magnitude and orientation. Observation demonstrates that these forces are real, quantifiable, and extreme, yet they do not conform to expectations grounded in ordinary magnetism. The behavior of magnetars challenges assumptions about stability and energy storage. You might think that energy is gradually released in predictable ways, but magnetars periodically emit bursts of gamma rays and X-rays that are sudden, brief, and highly energetic. These flares can release as much energy in a second as the sun emits in a century. Measurement confirms that the bursts are neither random nor chaotic. They are structured, sometimes recurring in patterns, yet they arise from mechanisms that remain only partially understood. The concentration of energy and the rapidity of its release imply internal processes that operate at scales of pressure, density, and magnetism beyond everyday comprehension. Observation also reveals that magnetars influence their surroundings in measurable ways. High-energy radiation ionizes nearby interstellar material, and the intense magnetic field shapes plasma flows across light years. Unlike ordinary stars, whose effects on the environment are gradual and continuous, magnetars act as concentrated sources of extreme energy. They produce detectable ripples in space, not only through radiation, but also through shifts in gravitational balance caused by the redistribution of mass and energy within the star. Instruments capture these effects, allowing precise reconstruction of the magnetar's behavior and its impact on the local galactic environment. The formation of such intense fields introduces further anomalies. Standard models of stellar evolution predict that neutron stars retain some magnetism from their progenitors, but the magnitudes observed in magnetars exceed expectations by orders of magnitude. Observation confirms that no incremental process alone can account for the concentration of energy. Instead, the field appears to emerge through mechanisms linked to the star's rotation, convection, and collapse, amplified in ways that produce measurable but counterintuitive extremes. Energy is confined and amplified in a self-reinforcing loop, suggesting that even small variations in initial conditions can lead to extraordinary divergence. Time is similarly distorted in the context of magnetars. The buildup of magnetic stress can occur over thousands of years, imperceptible in human terms, while the release occurs in milliseconds. The gamma ray bursts and X-ray flares carry a record of this temporal asymmetry, encoding energy accumulation over millennia into an instantaneous event. Observation allows you to measure the before and after, yet the internal sequence of events remains partially hidden, leaving gaps in understanding and a subtle unease about the processes unfolding beyond direct perception. Ultimately, magnetars demonstrate that energy can be concentrated, stored, and released on scales entirely removed from human intuition. Observation confirms that the universe is capable of producing structures in which physical forces operate at extremes both measurable and disturbing. Magnetic fields, energy release, and space-time distortions coexist in patterns that are consistent, quantifiable, and yet fundamentally alien. Magnators are evidence that even within familiar categories of stars, the universe can reach intensities and precision that challenge assumptions about scale, causality, and predictability. They stand as a reminder that measurement alone reveals the reality of extremes that cannot be experienced directly, forcing you to confront the indifferent magnitude of cosmic power. The ripples of gravity. Gravity seems constant, a force you experience every day. Yet gravitational waves reveal sudden distortions of space-time itself, rippling across the cosmos at light speed. These ripples are faint, almost imperceptible, yet they carry signatures of the most cataclysmic events, colliding black holes whose energies are inconceivable from a human perspective. From your vantage point on Earth, gravity feels uniform and predictable. Objects fall at steady rates, planets maintain their orbits, and stars appear anchored in familiar constellations. Measurement confirms this consistency in local contexts, reinforcing the notion of stability. Yet when a massive astrophysical event occurs far away, space-time itself flexes in response. Gravitational waves are disturbances that propagate outward, compressing and stretching space as they travel. The effect is subtle but measurable. Instruments detect shifts smaller than the diameter of a proton across kilometers of Earth-based detectors. Observation confirms that the universe communicates its most extreme events through distortions invisible to ordinary perception. These waves are produced by interactions involving extraordinary mass and acceleration. Binary black holes orbit one another, drawing closer over millions of years until the final merger. The collision converts several solar masses entirely into energy emitted as gravitational waves. Measurement shows that the signal carries information about the masses, spin, and orbital parameters of the black holes. The waves encode the dynamics of an event that is both unimaginably energetic and temporally brief. You can reconstruct the sequence of the collision. Yet the magnitude of the energy and the speed of space-time deformation remain fundamentally alien. Observation reveals that gravitational waves propagate without obstruction, passing through matter and energy, almost as if nothing exists to impede them. Their faintness belies the power of the events that generated them. A signal detected on Earth carries the imprint of a collision that occurred millions or even billions of years ago, a record of the universe's most extreme energies preserved across vast distances. The ability to measure these distortions introduces a paradox. Space-time, which you assume to be passive, is in fact a medium capable of dynamic, detectable movement. The familiar constancy of gravity is only a local approximation. On cosmic scales, it flexes, vibrates, and communicates. You might assume that events so distant would be irrelevant to local physics. Gravitational wave observation contradicts this assumption. Ripples passing through Earth subtly alter the separation of test masses in detectors, registering the imprint of energy that originated incomprehensibly far away. Measurement confirms the connectivity of the cosmos. Even the most isolated regions are linked through distortions in space-time, and the passage of time itself is encoded in the propagation of these waves. These are extreme events whose consequences extend beyond immediate observation, subtly reinforcing the universe's structure and dynamics. Time is revealed to be relative and flexible in a way you cannot sense directly. The waves encode the sequence and velocity of their originating events, preserving information about accelerations and orbital decay. Observation allows reconstruction of the process, Yet the flow of time is different for the colliding objects than for distant observers. Gravitational waves thus demonstrate that temporal experience is tied to measurement and location, a reminder that even forces assumed constant can manifest in ways that challenge your intuitive understanding of duration and causality. Ultimately, the ripples of gravity expose a universe in which the most extreme energy releases propagate through the very fabric of reality. Observation confirms that space is dynamic, responsive, and measurable, even in regions that appear empty. Gravitational waves connect distant cataclysms to local detectors, revealing a continuity of cause and effect that operates across unimaginable scales. You are confronted with the quiet realization that space-time is not inert. It is a medium, a messenger, and a record of extreme events, transmitting the energy and structure of the universe in ways that are detectable, precise, and profoundly alien to everyday experience. Colliding black holes. You expect massive objects to follow predictable orbits. When black holes merge, their behavior is quantifiable yet extreme. A single event converts several solar masses entirely into energy as gravitational waves, with consequences that echo through space. Observation shows that these events are precise, reproducible, and yet wholly outside normal experience. Binary black holes form when two massive stellar remnants enter mutual orbit, often over millions of years. From your perspective, their motion may appear regular, governed by the familiar rules of gravity. Yet precise measurement of their spiral reveals accelerations and interactions that are anything but ordinary. As the black holes approach, they distort each other's space-time, producing gravitational waves that encode the changing geometry of the system. Observation shows that even though the paths are governed by general relativity, the magnitudes of energy and curvature are extreme beyond intuitive understanding. The final merger is abrupt. The two singularities coalesce into a single, larger black hole, releasing energy equivalent to several solar masses in the form of gravitational waves. These waves propagate outward at the speed of light, stretching and compressing space-time along their path. Instruments on Earth, such as LIGO and Virgo, detect displacements smaller than a fraction of a proton, revealing the arrival of events that occurred billions of years ago. Observation confirms both the precision and scale of these events. The signal encodes mass, spin, and orbital configuration with fidelity. Yet the energies involved are so extreme that direct human experience offers no frame of reference. You might assume that such energy release would destroy or scatter matter in its immediate vicinity. Yet black holes interact primarily through gravity and gravitational radiation, leaving surrounding gas and stars largely undisturbed, unless they lie extremely close. Observation shows a universe in which catastrophic energy transformations can occur with minimal visible disturbance, a consequence of the unusual properties of space-time around black holes. What seems invisible or inert still carries measurable influence through gravitational waves, linking distant regions of space in subtle yet precise ways. The merger also illustrates the compression of time near extreme gravitational fields. From the perspective of the black holes themselves, the final moments of coalescence unfold in a fraction of a second. From a distant observer, the gravitational waveform arrives stretched, distorted by the curvature of space and cosmic expansion. Measurement allows reconstruction of the event sequence, yet the relativity of temporal perception introduces a dissonance between local and distant experience. Observation confirms that time, mass, and energy are interdependent in ways that defy everyday intuition. Patterns in colliding black holes are striking. Despite their extremity, the mergers are reproducible. waveforms follow theoretical predictions based on general relativity with remarkable fidelity. Yet, the parameters vary widely. Mass ratios, spin orientation, and orbital eccentricity all influence the resulting gravitational waves, producing measurable differences in shape and intensity. Observation provides a catalog of events, each consistent with physical law, yet each unique in its configuration, underscoring the combination of predictability and extremity that defines the universe at its most energetic. Ultimately, colliding black holes demonstrate that the cosmos operates at scales of energy, mass, and curvature that are measurable yet entirely alien. Observation confirms the existence of processes in which matter disappears, energy propagates through space-time, and time itself is flexed without violating the underlying laws of physics. The events are precise, repeatable, and consistent with theory, yet wholly outside human experience, leaving you with the quiet recognition that the universe's most extreme phenomena unfold with deterministic rigor in domains beyond intuition. The measurable, structured violence of these mergers redefines your assumptions about stability, continuity, and the limits of perceivable force. The brightest flashes. Astronomers measure intensity and luminosity, assuming upper limits. Some bursts exceed these by orders of magnitude. They are observable across billions of light years, and their brief appearance implies processes that concentrate energy in ways standard astrophysical models struggle to fully explain. Measurement confronts expectation, leaving interpretation open-ended. From your perspective on Earth, brightness is a familiar concept. Sunlight illuminates a room, distant stars twinkle predictably, and even transient events like novae are moderate and comprehensible. Yet the brightest cosmic flashes defy this intuition. Observations using gamma-ray and X-ray telescopes detect events that momentarily outshine entire galaxies. The intensity is extreme and concentrated, lasting from milliseconds to a few minutes. Measurement confirms that the energy is not diffuse. It is tightly focused in both time and space. What seems like a simple flash of light is a record of energy release at a scale that challenges conventional models of stellar physics. The brevity of these flashes belies the total energy involved. While a star may shine steadily for billions of years, these bursts concentrate equivalent energy in an instant. Light curves reveal intricate substructure within each event, peaks, troughs, and micro-variations that suggest a mechanism that is organized, precise, and energetic. Observation demonstrates that extreme energy can be channeled into forms that are coherent yet fleeting, revealing a universe capable of compressing both magnitude and temporality in ways that exceed human expectation. The sources of the brightest flashes vary, yet all involve extremes of mass, gravity, and magnetic field. Collapsing massive stars, neutron-star mergers, and interactions in active galactic nuclei produce emissions detectable across cosmological distances. Measurement allows reconstruction of their origins, yet the processes remain partially opaque. Energy is released in jets or beams that are highly collimated, often directed along narrow angles that align with Earth purely by chance. Observation reveals that what is detected is only a small fraction of the total events occurring in the universe. The cosmos produces flashes of unimaginable intensity routinely, yet most go unnoticed because of geometric orientation and distance. Even the propagation of light from these events carries anomalies. Interactions with interstellar and intergalactic media, as well as relativistic effects from space-time curvature, introduce subtle shifts in wavelength, intensity, and timing. Instruments can measure these variations, revealing not only the source's properties, but also the structure of the space it traversed. The flash becomes a messenger, encoding both energy and the environment through which it has traveled. Observation exposes a network of cause and effect, linking extreme events to distant regions of the cosmos. Temporal scale is equally extreme. Milliseconds of emission encode processes that unfolded over years or millennia within the progenitor system. The event appears instantaneous, yet its physical precursors were prolonged, gradual, and largely imperceptible. Measurement bridges these scales, connecting human perception of a brief flash to the long-term dynamics that generated it. Observation demonstrates that time, energy, and intensity are intertwined in ways that defy ordinary intuition. The briefest events can carry the weight of entire stellar histories. Ultimately, the brightest flashes reveal a universe that concentrates energy with precision, brevity, and intensity far beyond everyday expectation. Observation confirms that the cosmos produces phenomena whose scale, temporal compression, and coherence challenge existing models, forcing you to confront extremes that are measurable yet alien. Light, which you assume to travel steadily and predictably, becomes a record of violent, transient processes operating at the limits of physics. These flashes are precise, structured, and extreme, leaving no ambiguity about their reality, yet leaving their underlying mechanisms only partially understood. Measurement, rather than simplifying, heightens the paradox. The universe can be both orderly and overwhelmingly extreme simultaneously. Neutron star collisions. Neutron stars are dense, cold, and stable, or so it seems. When two collide, they create kilonova that radiate heavy elements, gravitational waves, and gamma rays. Observation confirms synthesis of gold and platinum in moments, a direct challenge to the notion that such elements accumulate slowly over time. The cosmos accelerates processes you consider gradual. From your perspective, neutron stars appear inert and unchanging. Their mass is immense, their radius is small, and their density is extreme, so dense that a sugar cube-sized volume would weigh billions of tons. Yet measurement shows that even these seemingly stable objects harbor latent potential for extreme transformation. Binary neutron star systems slowly lose energy through gravitational radiation, causing orbits to decay over millions of years. You might expect a gradual convergence, but when the collision occurs, the event is sudden, violent, and precisely measurable. Observation confirms that the universe can store immense potential energy for eons, then release it in a single, coherent burst. The collision produces a kilonova, a luminous event distinct from ordinary supernovae. Gamma-ray telescopes detect bursts lasting seconds, while optical and infrared instruments track material ejected over days. The energy released is concentrated, yet structured. Photons, neutrinos, and gravitational waves propagate outward, each carrying measurable information about the event's dynamics. Observation reveals that the matter expelled is rich in heavy elements, the very atoms you consider rare and slowly formed. Gold, platinum, uranium are synthesized almost instantaneously during the merger. Measurement demonstrates that processes once assumed slow and cumulative can occur on cosmic timescales equivalent to a heartbeat. Gravitational waves accompanying the collision provide further insight. Instruments detect the minute distortions of spacetime caused by the stars in spiral and merger, allowing precise reconstruction of mass, spin, and orbital eccentricity. These measurements confirm that energy and momentum are conserved in extreme conditions, yet they also reveal the universe's capacity to manipulate matter and energy in ways inaccessible to direct experience. Time appears compressed, Events that unfold over milliseconds from the star's perspective encode millennia of energy accumulation, and your instruments record them as coherent, interpretable signals. Observation also shows that kilonovae influence their surroundings. Heavy elements are ejected at relativistic speeds, enriching the interstellar medium and seeding future generations of stars and planets. Radiation and shockwaves propagate outward, interacting with gas and dust across light years. What seems instantaneous in appearance carries prolonged consequences across space and time, demonstrating that extreme events are not isolated. They link the local and cosmic environment through measurable, structured effects. The implications for your understanding of causality are subtle but profound. Neutron star collisions demonstrate that stability is a temporal construct. Objects you perceive as static can harbor immense potential, released suddenly in ways that reshape surrounding space. Measurement confirms that the universe balances long periods of apparent stillness with rapid, extreme transformation, encoding both in observable signals. These events are reproducible in theory and consistent with physical laws, yet they remain alien to intuition. Ultimately, neutron star collisions illustrate a universe in which time, energy, and matter operate on scales that challenge human perception. Observation confirms that processes you assume gradual can occur instantaneously, that matter can be synthesized in extraordinary quantities in a single event, and that gravitational waves communicate extreme energy across vast distances. The cosmos accelerates its own evolution in ways measurable yet disorienting, demonstrating that even the densest, coldest, most stable objects can transform abruptly. You are confronted with a reality where continuity is deceptive, where accumulation is sudden, and where the universe operates with both precision and extremity, beyond ordinary comprehension. The stretch of light. Light from distant events is redshifted by cosmic expansion, a predictable consequence of relativity. Yet the intensity and timing of extreme events reveal inconsistencies in apparent distance and energy. Observation exposes subtle contradictions between your measurements and the scale of causality, highlighting that even light carries anomalies when measured precisely. From your perspective, light is a reliable messenger. It travels at a constant speed, conveys information across vast distances, and encodes the physical properties of the objects it encounters. Measurement underpins this expectation. You can determine temperature, composition, velocity, and distance with confidence, relying on the predictable propagation of photons. Yet when observing the universe's most extreme events, gamma-ray bursts, kilonovae, supernovae, the light that arrives challenges this assumption. Intensities exceed predictions, and timing of arrival diverges from expectation, revealing discrepancies between the measured energy and inferred distance. Observation demonstrates that even the simplest, most familiar phenomenon, light, can encode complexities that are subtle, measurable, and disorienting. Redshift is a primary tool for measurement, used to determine cosmic distance based on the stretching of wavelength. Yet extreme bursts sometimes appear brighter or fainter than their redshift alone predicts. Instruments detect intensity variations that imply energy output inconsistent with naive calculations of distance and luminosity. These discrepancies are not errors. They are signatures of relativistic beaming, gravitational lensing, or unobserved interactions along the light's path. Observation confirms that photons carry information not only about the source, but also about the structure of space through which they propagate. Light becomes both signal and record, revealing processes that are coherent, quantifiable, yet counterintuitive. The timing of light's arrival further complicates interpretation. High-energy photons can precede or lag behind lower-energy emissions from the same event. Observations of gamma-ray bursts demonstrate structured microsecond variations in emission, encoded in a stream of photons traveling billions of light-years. Measurement allows reconstruction of the event sequence, yet apparent simultaneity breaks down under scrutiny. Even light, which you assume to travel uniformly, encodes discrepancies in both energy and chronology. The universe uses its most fundamental constant to deliver a record that is simultaneously precise and subtly contradictory. Observation also reveals the interaction of light with space-time itself. Gravitational fields warp paths, altering arrival times, frequency, and apparent location. Light curves and spectra carry traces of these distortions, enabling you to measure gravitational influences that are otherwise invisible. These effects are measurable, repeatable, and entirely consistent with general relativity, yet they introduce anomalies in perceived distance and energy. What you interpret as simple propagation is actually a complex record of cosmic structure, curvature, and the sequence of extreme events. Ultimately, the stretch of light demonstrates that measurement, even of the most familiar phenomenon, can uncover inconsistencies in scale, causality, and energy distribution. Observation confirms that light is not a passive transmitter, but an active archive of extreme processes and intervening structures. Photons traveling across billions of years encode both the history of their source and the medium through which they travel, leaving a record that is simultaneously coherent, precise, and subtly discordant. Even the speed of light, the foundation of measurement and expectation, reveals the universe's capacity to concentrate complexity in a form that is both measurable and alien to intuition. The universe communicates through light with exactitude that exceeds comprehension, yet that exactitude uncovers subtle contradictions. Intensity, timing, and spectral distribution all challenge the assumptions of distance, energy, and causality. Observation leaves you with the realization that the most fundamental constant of nature, the propagation of light, is simultaneously the messenger and the anomaly, a measurable thread linking extreme events to your instruments, while revealing the universe's subtle capacity to defy intuitive expectations. Light, in its extremes, stretches not only across space, but also across the limits of comprehension, carrying within it a record that is precise, unsettling, and fundamentally complex. Jets from black holes. Accretion disks funnel matter into relativistic jets that extend for thousands of light years. You might expect matter to fall inward, yet observation shows it expelled in tightly collimated beams at near light speed. These jets are stable in direction but variable in energy, a combination that undermines simple models of stellar collapse. Black holes are defined by their singularity and event horizon, regions from which nothing, not even light, can escape. Surrounding many of them are accretion disks, dense swirls of matter spiraling inward. Observation confirms that most of this material does not simply fall into the singularity. Instead, magnetic fields in the disk redirect angular momentum and energy, producing narrow, focused jets of plasma that escape along the rotational axis. These jets are observable across immense distances, their radiation spanning radio waves, X-rays, and gamma rays. Measurement shows that the expelled material travels at velocities approaching the speed of light, maintaining coherence over thousands of light years. You might assume that matter falling toward a black hole is inevitably lost, that energy is dissipated uniformly or absorbed, yet instruments reveal highly organized structures within these jets. Observations show shock fronts, knots, and helical twists along the jet's length, each feature measurable in position, velocity, and emitted radiation. These structures indicate that the ejection is not chaotic. Despite originating in a region of extreme gravity and curvature, the jets maintain directional stability and internal coherence over vast distances. Observation demonstrates that extreme forces can produce both violent and ordered outcomes simultaneously. The energy output of these jets is variable. Long-term monitoring reveals fluctuations in luminosity, emission spectra, and particle density. Sometimes the jet brightens dramatically for days or weeks, then fades, only to intensify again. Measurement confirms that these variations are tied to changes in accretion rate, disk instabilities, or magnetic reconnection events. The result is a phenomenon that is predictable in broad terms, but chaotic in detail, combining determinism and randomness in a measurable, yet unsettling, pattern. The jets are both ordered and extreme, stable and volatile, illustrating the universe's capacity to balance conflicting properties. Observation also shows the interaction of jets with surrounding space. As the plasma collides with interstellar medium, it produces bow shocks, heats gas, and generates secondary radiation that can be measured at multiple wavelengths. These interactions are spatially extended, producing observable cavities and lobes in radio galaxies. Light from these interactions encodes information about energy, density, and composition, revealing processes that continue far beyond the immediate region of the black hole. Measurement demonstrates that even a single jet is not localized. It influences structure, motion, and composition across thousands of light years. Time is compressed and extended simultaneously in these systems. Material is expelled near instantaneously relative to the black hole's frame, yet the propagation across interstellar distances unfolds over millennia. Observation allows you to reconstruct sequences of ejection and interaction, bridging microsecond events with processes that shape galactic-scale structures. Measurement confirms that extreme energy releases can operate on multiple temporal scales concurrently, a dissonance between intuitive perception and cosmic reality. Ultimately, jets from black holes reveal a universe in which matter, energy, and space-time interact with precision and extremity. Observation confirms that gravity and magnetism can organize matter into narrow, coherent, relativistic streams while simultaneously producing variable energy outputs. The phenomenon is measurable, structured, and reproducible, yet it defies expectations grounded in simpler models of accretion and collapse. The universe produces extremes of velocity, energy, and scale in ways that are simultaneously predictable and alien, leaving you with the quiet, persistent awareness that even matter destined for oblivion can be redirected with precision, sculpting space across cosmic distances while challenging all assumptions about stability, directionality, and energy distribution. Tidal disruption. Events. Stars wandering too close to black holes are torn apart by tidal forces. You assume mass is conserved locally, yet measurements reveal matter accelerated, radiating, and partially ejected back into space. Observation confirms that energy and matter behave in extreme ways when caught in the gravitational grip of compact objects. From your perspective, stars are stable, coherent spheres of plasma, bound by gravity and internal pressure. Their behavior is predictable on human timescales. Fusion balances collapse, light is emitted steadily, and orbital dynamics are measurable. Yet, when a star approaches a black hole's tidal radius, these assumptions collapse. Observation shows that differential gravitational forces stretch and compress the star, producing intense heating and shockwaves. The star is elongated into a stream of matter, with a fraction falling inward toward the event horizon, while other portions are flung outward at high velocities. Measurement confirms that mass is redistributed violently, energy is amplified, and matter behaves in ways counterintuitive to everyday experience. The dynamics of these events are extreme. As stellar material spirals into the black hole, gravitational energy converts into radiation, producing intense flares detectable across billions of light years. X-ray and ultraviolet telescopes record sharp peaks and decays in luminosity, revealing that the energy release is structured and quantifiable. Observation shows that the luminosity, while extreme, is correlated with the mass and trajectory of the disrupted star, allowing you to reconstruct both the event and the black hole's properties. Yet the scale and rapidity of energy release defy conventional intuition. Minutes of observation encode centuries of gravitational work. Matter expelled from tidal disruption events behaves unpredictably yet measurably. Some fraction forms accretion streams that later produce relativistic jets, while other matter escapes the system entirely. Instruments detect high-velocity outflows, including gas moving at significant fractions of light speed. These ejected streams interact with the surrounding interstellar medium, creating shocks, heating gas, and emitting radiation that can be traced across multiple wavelengths. Observation confirms that the influence of a single stellar encounter extends far beyond the immediate region, linking microscopic gravitational interactions to structures spanning light years. Time is both compressed and expanded in tidal disruption events. The final moments of infall occur in minutes or hours, yet the disrupted debris continues to radiate and interact for years. Light curves and spectral evolution preserve the sequence of events, allowing precise reconstruction. Measurement demonstrates a temporal asymmetry. Energy accumulation occurs over the star's lifetime, yet release and redistribution occur nearly instantaneously. The universe compresses processes you perceive as slow into observable extremes, revealing mechanisms that operate simultaneously on micro and macro scales. Observation of tidal disruption events also exposes subtleties in causality and energy conservation. Matter does not simply vanish, it is transformed into radiation, kinetic energy, and reorganized streams of plasma. The system is highly deterministic, yet the interplay of orbital dynamics, relativistic effects, and magnetic fields introduces complexity that ensures each event is unique. Measurement confirms both predictability and novelty, revealing patterns without eliminating uncertainty. The physics is measurable and consistent, yet the outcome is extreme and alien to intuition. Ultimately, tidal disruption events illustrate that the universe is capable of simultaneously destroying and redistributing matter in highly structured, measurable ways. Observation confirms that gravitational extremes not only manipulate mass and energy, but do so while preserving signatures of process and causality. You witness matter accelerated to relativistic velocities, energy concentrated into radiation detectable across vast distances, and temporal sequences encoded in light and plasma. Even the most familiar constituents of the cosmos, the stars, can be transformed violently, predictably, and extraordinarily when subjected to the gravitational extremes of black holes. The universe, through these events, reveals its capacity to operate with both precision and extremity, challenging every assumption about stability, mass, and energy distribution. The longevity of shockwaves explosions propagate through space, and shockwaves persist far longer than intuitively expected. Supernova remnants expand for thousands of years, influencing surrounding gas and star formation. Observation indicates that energy dissipates unevenly, creating structured chaos that defies assumptions about smooth distribution over time. From your perspective, energy released in a cosmic explosion might be expected to spread evenly, fading predictably with distance. Light from a supernova can be seen across millions of light years, yet the kinetic energy of expelled material interacts with its environment in ways that produce far more complex outcomes. Instruments detect filaments, bubbles, and cavities in the interstellar medium, revealing that energy does not diffuse uniformly. Observation confirms that the remnants of explosions preserve structure over millennia, encoding the history of the event in both space and motion. Shockwaves propagate through heterogeneous media, and this heterogeneity affects the distribution of energy. Dense clouds slow expansion locally, while less dense regions allow material to travel farther at higher velocity. Measurement shows that these variations produce anisotropies in shape and density, creating patterns that are consistent, measurable, and yet non-intuitive. A single explosion can sculpt structures across tens of light years, compressing some regions to trigger star formation, while leaving others virtually untouched. Observation confirms that cosmic energy is neither evenly dissipated nor entirely chaotic. It is structured, extreme, and consequential. Timescales involved in shockwave propagation are also surprising. The initial explosion occurs over hours or days, but its physical influence unfolds over millennia. Observing supernova remnants allows you to reconstruct centuries of interaction from spatial patterns and velocities. Measurement provides a temporal bridge between brief catastrophic events and their prolonged consequences, revealing a universe where cause and effect are separated not only by space, but by scale and duration. Shockwaves serve as both agents of change and archives of their originating events, preserving measurable information long after the initial release of energy. The interactions of shockwaves with magnetic fields and cosmic rays further complicate the picture. Electromagnetic fields guide the flow of charged particles, producing filamentary structures detectable in radio and X-ray observations. Cosmic rays accelerated by the shocks travel vast distances, influencing regions far beyond the immediate remnants. Observation shows that energy is transferred and transformed, not simply dispersed, resulting in complex and measurable consequences across the interstellar medium. The remnants are a record of both violent release and ongoing dynamical evolution, illustrating the universe's capacity to encode structure in processes that appear at first glance to be random. Shockwaves also reveal subtleties in measurement and perception. The apparent boundary of a remnant does not correspond to a simple edge of influence. Matter and energy extend beyond visible filaments, detectable through velocity, ionization, and radiation signatures. Observation demonstrates that energy is both local and extended, concentrated in structures while leaving diffuse effects in surrounding regions. You measure the shockwave and interpret its shape, yet the full scale of its influence remains only partially accessible, a continuous reminder of the limitations of perception and instrumentation in capturing cosmic processes. Ultimately, the longevity of shockwaves illustrates that even when energy is violently released, it is neither entirely dispersed nor entirely stable. Observation confirms that explosions leave coherent, measurable imprints that evolve over millennia, shaping both matter and space in structured yet unpredictable ways. Shockwaves connect temporal extremes, the brief initial event with prolonged, spatially extended consequences, revealing that energy in the cosmos is both dynamic and archival. You are confronted with the realization that even violent phenomena, which appear instantaneous and destructive, propagate their influence in measured, structured, and long-lasting ways, leaving an indelible mark on the cosmos that challenges assumptions about smoothness, dissipation, and uniformity of energy in space and time. Cosmic rays, particles that travel light years. High-energy particles bombard Earth constantly. Their origin, often linked to distant supernovae or active galactic nuclei, is measurable yet indirect. Observation shows that matter itself carries the memory of extreme events across light years, challenging assumptions about local causality and the isolation of space. From your perspective, space appears mostly empty, a vacuum between stars and galaxies. Yet cosmic rays, composed of protons, atomic nuclei, and high-energy electrons, travel through this apparent void, connecting distant regions of the universe with measurable impact. Detection instruments on Earth record a steady flux of particles, their energies ranging from modest to extreme, sometimes exceeding 10 to 20 electron volts. Measurement confirms that these particles are remnants of violent events, carrying information about astrophysical phenomena that occurred millions or billions of years ago. They are messengers of energy, encoded in matter rather than light. The journey of cosmic rays is shaped by interactions with interstellar and intergalactic magnetic fields. Their paths are deflected, bent, and occasionally trapped, producing arrival patterns at Earth that are stochastic yet analyzable. Observation reveals that while the precise trajectory of an individual particle may be unpredictable, statistical distributions encode properties of the source and intervening medium. Even as they traverse space seemingly at random, cosmic rays preserve measurable signatures of extreme astrophysical processes, including shock acceleration in supernova remnants and jets from active galactic nuclei. Measurement allows you to reconstruct these origins indirectly, demonstrating that matter itself, not only light, conveys information across vast distances. The energy of cosmic rays challenges intuition. Some particles carry kinetic energy equivalent to that of a well-hit baseball, concentrated in a single subatomic particle. Observation confirms that the universe routinely produces concentrations of energy at scales vastly exceeding terrestrial experience. These high-energy events are localized at the source, yet their effects propagate across light years, arriving at Earth in a measurable flux. You are confronted with the quiet paradox that extreme processes leave enduring physical traces, linking spatially isolated regions in ways that defy everyday notions of causality and distance. Cosmic rays also reveal subtleties in temporal perception. The particles arriving at Earth today may have been accelerated millions of years ago. Measurement encodes a time bridge between distant astrophysical events and contemporary detection, illustrating that matter itself carries a historical record. Observation shows that even as the particles interact with planetary atmospheres, generating showers of secondary particles, their energy, composition, and direction retain measurable information about origins, acceleration mechanisms, and intervening space. You can reconstruct these histories, yet the underlying processes remain distant, extreme, and alien to intuition. Furthermore, cosmic rays influence local environments. Their interaction with the atmosphere produces ionization, contributes to cloud formation, and even affects electronics in satellites. Observation demonstrates that a particle originating from a supernova or galactic jet can have measurable effects on systems light years away from its source, linking astrophysical extremes to terrestrial experience. Measurement confirms the non-locality of cosmic phenomena. What seems isolated or remote is continuously connected through the transport of matter and energy. Ultimately, cosmic rays illustrate that space is not an inert void. Observation confirms that matter itself carries signatures of extreme events, traveling vast distances with measurable consequences. The universe encodes energy, history, and structure within these particles, connecting distant astrophysical violence to local measurement. You are confronted with the realization that energy can propagate through space via matter as effectively as through light, challenging assumptions about isolation, causality, and the limits of influence. Even in the emptiest regions, the cosmos communicates in subtle, measurable ways, linking events across space and time through streams of high-energy particles that defy ordinary expectation while preserving coherent, detectable traces of extreme processes. Hypernovae. Beyond expectations. Some stellar explosions release an order of magnitude more energy than conventional supernovae. You expect limits, yet observation confirms exceptions. These events challenge models of stellar evolution and nuclear synthesis, revealing a cosmos capable of transient, concentrated extremes without warning. From your perspective, massive stars end their lives in processes that, while dramatic, remain bounded by the physics of fusion, gravity, and pressure. Supernovae are extreme yet predictable, distributing energy and material over observable timescales. Hypernovae defy this expectation. Observation shows explosions releasing 10 times the energy of a standard supernova, producing intense gamma-ray bursts and powerful shockwaves that travel across interstellar space. Measurement confirms that these events concentrate energy in a manner that is both measurable and extreme, defying conventional assumptions about stellar limits. The progenitors of hypernovae are typically massive, rapidly rotating stars. Their cores collapse under gravity, forming black holes almost immediately. Observation reveals that the collapse is highly directional, producing collimated jets along the rotational axis. These jets expel energy and matter at relativistic speeds, observable as gamma-ray bursts, detectable billions of light-years away. Measurement shows that the jets are structured and coherent, carrying energy far beyond what is expected from ordinary supernova mechanisms. Extreme rotation and magnetic fields amplify the concentration of energy, creating a phenomenon that is at once orderly and violent. Light curves and spectra provide precise records of these events. Observation demonstrates complex temporal structures, multiple peaks, rapid rises, and extended tails, each corresponding to processes within the collapsing star and its ejected material. The spectrum of emitted elements shows anomalies compared to typical supernovae, enhanced production of certain heavy elements, unusual isotopic ratios, and unexpected nuclear products. Measurement confirms that hypernovae are not simple amplifications of supernova. They are qualitatively distinct, demonstrating that the universe can accelerate and intensify processes considered gradual or bounded. The spatial influence of hypernovae is significant. Shockwaves propagate through surrounding gas clouds, compressing material, triggering star formation, or dispersing gas depending on local density. Relativistic jets inject energy into regions tens of light-years across, measurable in both radiation and kinetic motion of matter. Observation shows that hypernovae are not isolated phenomena. They actively shape galactic structure and evolution, leaving measurable signatures in the interstellar medium long after the initial explosion. The interplay of energy, mass, and environment demonstrates that even transient events can have enduring, far-reaching consequences. Temporal compression adds further complexity. The formation of a black hole, the launch of relativistic jets, and the release of gamma rays occur on timescales of seconds to minutes. Yet the after effects of the event unfold over thousands of years. Observation allows reconstruction of these sequences through measurement of emitted radiation, shock propagation, and elemental composition. The contrast between the instantaneous release of extreme energy and the prolonged influence on the surrounding environment underscores the universe's capacity to operate across simultaneous temporal scales, producing both immediate and extended effects. Ultimately, hypernovae demonstrate that the universe possesses mechanisms for transient yet concentrated extremes that are measurable, coherent, and highly impactful. Observation confirms that energy, matter, and radiation can be accelerated to limits beyond expectation, reshaping local and distant environments. You are confronted with the reality that stellar processes are not merely bounded by mass and rotation. They can exceed predictable thresholds, producing phenomena that are both deterministic in structure and alien in extremity. Hypernovae exemplify the cosmos's capacity to balance precision and violence, concentration and dispersion, brevity and enduring influence, leaving measurable imprints that challenge assumptions about the scale and intensity of astrophysical processes. The gamma-ray afterglow. After a burst, radiation lingers in multiple wavelengths. This afterglow is observable and predictable in shape, yet defies simple energy accounting. The total output exceeds expectations based on initial mass. Measurement exposes a mismatch between cause and observable effect, a subtle violation of intuitive conservation. From your perspective, energy released in an astrophysical event should correspond predictably to the mass involved and the mechanisms driving the release. Light, radiation, and particle emission are constrained by these factors. Yet the afterglows following gamma-ray bursts challenge these assumptions. Observations reveal persistent emission in X-ray, ultraviolet, optical, and radio wavelengths, extending from hours to weeks after the initial burst. The intensity, duration, and spectral distribution do not always align with naive calculations of the progenitor's mass or energy output. Measurement confirms that the system produces effects that appear disproportionately large relative to the input, suggesting processes that concentrate, redistribute, or prolong energy release beyond intuitive expectation. The temporal structure of the afterglow is revealing. Light curves show gradual decay, punctuated by flares or plateaus, patterns reproducible across multiple events. Each variation carries information about the density of the surrounding medium, magnetic field interactions, and relativistic dynamics. Observation demonstrates that the afterglow is not a simple tale of emission, but a structured phenomenon, encoding both the properties of the original explosion and the environment into which it expands. The persistence of energy across different wavelengths indicates that the initial burst sets in motion processes that continue independently, propagating effects long after the source has ceased its initial activity. Spatial interactions are equally consequential. Expanding shock fronts collide with interstellar gas, generating synchrotron radiation detectable across light years. Jets initially confined to narrow angles broaden and interact with surrounding material, producing measurable secondary emission. Observation confirms that energy is neither confined nor isotropic. It redistributes dynamically according to environmental conditions. Measurement of afterglow geometry and intensity provides indirect yet precise information about both the progenitor system and the interstellar medium. The universe encodes its history in observable radiation, linking cause and consequence across distance and time. The underlying physics of afterglows emphasizes extreme relativistic effects. particles accelerated to near light speed emit radiation that is beamed and time compressed, producing the appearance of prolonged emission from a source that is itself brief. Measurement allows reconstruction of these relativistic dynamics, revealing that the apparent energy output is amplified by geometry, velocity, and magnetic field interactions. Observation confirms that intuitive notions of cause, effect, and energy distribution can be misleading when relativistic conditions dominate. The afterglow is simultaneously predictable and counterintuitive, coherent in structure, yet extreme in effect. Ultimately, the gamma-ray afterglow illustrates that even when an event appears over, its influence persists and evolves in measurable ways. Observation confirms that energy does not dissipate simply or evenly. It transforms, interacts, and propagates according to processes that are both well-defined and alien to ordinary perception. You are confronted with the subtle paradox that radiation can outlive its immediate cause, carrying signatures of magnitude, structure, and interaction that exceed expectations. Measurement reconciles the afterglow with physics, yet it leaves a lingering unease. The universe produces effects that are coherent, measurable, and observable, yet disproportionate relative to intuitive notions of cause and mass energy. Even in its decline, a gamma-ray burst continues to reveal the cosmos's capacity to concentrate, redistribute, and extend energy, demonstrating that extremity is not confined to instantaneous events, but persists across time and space, encoded in observable light and radiation. Cosmic scale collisions. Galaxies collide over millions of years, appearing graceful from afar. Yet precise observation of starburst activity, gravitational wave emission, and black hole interactions reveals violent internal dynamics. Scale does not diminish extremity. Instead, energy concentrates in ways that magnify rather than average out. From your perspective, galaxies seem vast, diffuse, and stable structures, moving slowly across the cosmic web. You might assume that when two galaxies merge, the immense scale would smooth out violent interactions, producing gradual and predictable outcomes. Observation contradicts this expectation. Instruments detect bursts of star formation, triggered as gas clouds collide and compress under tidal forces. Measurements of radiation reveal regions of intense energy release, where new stars ignite simultaneously, creating localized extremes within the seemingly slow evolution of the system. Even on a scale of hundreds of thousands of light years, energy concentrates rather than diffuses. The central, supermassive black holes of colliding galaxies contribute to extreme dynamics. As galactic cores approach, gravitational interactions perturb orbits and funnel gas toward the central regions. Observation shows that accretion rates increase dramatically, producing powerful flares, relativistic jets, and high-energy radiation. Measurements confirm that these emissions are coherent, directional, and sustained, yet they arise from processes that are entirely internal and unobservable from casual inspection. The apparent calm of a galaxy's shape masks extreme transformations occurring within. Gravitational waves provide a further measure of internal violence. When black holes merge as a result of galactic collisions, ripples in space-time propagate outward, encoding information about mass, spin, and orbital dynamics. Observation confirms that these waves carry energies equivalent to several solar masses converted entirely into space-time distortion. You measure an event lasting seconds, yet the consequences extend across millions of light years, influencing surrounding matter through gravitational interaction. Scale does not dilute extremity. Instead, the larger the system, the more energy is concentrated and encoded in measurable signals. Starburst regions illustrate another subtle paradox. Gas clouds that might seem diffuse under casual observation condense rapidly under tidal compression, forming clusters of massive stars. Radiation, stellar winds, and supernovae from these clusters further energize the surrounding medium. Measurement reveals feedback loops. Localized concentrations of energy generate further turbulence, accelerating star formation and dispersing gas irregularly. Observation demonstrates that even in an apparently smooth, large-scale system, matter and energy organize into patterns of extreme intensity and coherent structure. Time complicates perception further. The collision itself spans millions of years, but localized phenomena, supernova, black hole mergers, jet emissions, occur over seconds to centuries. Instruments allow you to reconstruct these nested timescales from light and gravitational signals, revealing a hierarchy of processes operating simultaneously across space and time. Measurement demonstrates that cosmic events are neither uniform nor linear. Extreme processes are embedded within the slow evolution of the system, producing surprises that cannot be inferred from the global scale alone. Ultimately, cosmic scale collisions reveal a universe in which size does not mitigate violence or energy concentration. Observation confirms that galactic mergers combine graceful visual motion with localized, measurable extremes: concentrated star formation, relativistic jets, gravitational waves, and energetic feedback loops. You are confronted with the realization that scale amplifies complexity, producing events that are both predictable in outcome and alien in intensity. Energy is neither uniform nor averaged over distance. It is directed, concentrated, and encoded in structures that persist and propagate across space and time. Colliding galaxies, while visually slow and smooth, exemplify a cosmos in which extremity is nested within vast scales, measurable yet fundamentally counterintuitive to human perception. Extreme mass ratio in spirals. Compact objects orbiting supermassive black holes generate gravitational waves that encode intricate orbital mechanics. Observation allows reconstruction of paths, yet the data imply forces and accelerations beyond ordinary human comprehension. Your expectations of smooth orbital decay are inadequate for these measurements. From your perspective, orbital motion is simple and predictable. Planets circle stars, moons circle planets, and larger objects move under familiar gravitational laws. Yet when a small, dense object, a neutron star or stellar mass black hole, orbits a supermassive black hole, these assumptions break down. Observation reveals extreme precession, tidal stretching, and relativistic frame dragging, all measurable through the emitted gravitational waves. The orbit is neither smooth nor uniform. It encodes subtle, precise perturbations that can only be deciphered through long-term, high-precision observation. Measurement shows that the apparent simplicity of orbital decay conceals a hierarchy of forces operating at scales and intensities beyond intuitive comprehension. The gravitational waves themselves carry a record of the system's dynamics. Instruments detect oscillations in space-time, subtle distortions that correspond to each turn of the smaller object around its massive companion. Observation allows reconstruction of orbital eccentricity, inclination, and relativistic precession, yet these measurements reveal that energy and angular momentum exchange in highly complex patterns. The inspiral is gradual over thousands of orbits, but each orbit produces measurable deviations from classical predictions. Your expectation that gravity operates smoothly on all scales is undermined. The data show deterministic, extreme, and locally amplified effects produced by space-time curvature. Tidal forces during the inspiral are profound. The smaller object experiences stretching and compression, measurable in principle by the emitted gravitational waves, even though direct observation of physical deformation is impossible. Observation confirms that the extreme curvature near the supermassive black hole enhances these effects, producing orbital shifts that cannot be captured by Newtonian mechanics. Measurement allows you to calculate precise trajectories, yet the accelerations involved and the tidal forces acting over time are orders of magnitude beyond terrestrial experience, creating a system that is simultaneously predictable and alien. Relativistic effects amplify the complexity. Frame dragging twists spacetime around the black hole's rotation, causing the orbit to precess in ways that deviate from standard expectations. Gravitational redshift and time dilation alter the frequency and apparent timing of emitted waves. Observation confirms that these phenomena are measurable and reproducible, yet they produce dynamics that seem counterintuitive. The orbiting body accelerates and decelerates in ways that violate naive assumptions about smooth decay, producing intricate signatures encoded in the gravitational wave signal. The system also demonstrates an interplay of scale and time. The inspiral may last millions of years in total, yet each orbit generates minute, detectable perturbations in spacetime. Observation allows you to extract temporal patterns from the gravitational waves, linking the microscale oscillations of spacetime with the macroscale evolution of the orbit. Measurement reveals that the passage of time and energy exchange is not uniform. The system operates simultaneously on multiple temporal layers, bridging short-term variations with long-term evolution. Ultimately, extreme mass ratio inspirals reveal a cosmos in which orbital mechanics are precise, measurable, and yet profoundly alien. Observation confirms that matter can move under forces and accelerations beyond human intuition, producing gravitational waves that encode both deterministic structure and extreme intensity. You are confronted with the realization that even seemingly simple orbital systems conceal hierarchical complexity, where scale, relativity, and gravity conspire to produce measurable phenomena that challenge assumptions about smooth motion, decay, and energy exchange. The universe demonstrates its capacity to combine predictability with extremity, order with alien mechanics, revealing a layer of reality accessible through measurement but beyond direct comprehension. The limits of light. Travel events at cosmological distances allow you to see the past directly, yet simultaneous measurement of energy and timing in extreme events shows constraints on how much you can infer about the present. Observation introduces paradox. The farther you look, the less direct control you have over interpretation. From your perspective, light is a messenger. Photons travel across space, conveying information about distant sources. You assume that by measuring intensity, wavelength, and timing, you can reconstruct the state of the universe at the moment of emission. Yet the practical limitations of observation complicate this assumption. Light is subject to cosmological redshift, gravitational lensing, and scattering, all of which alter the signal before it reaches your instruments. Measurement reveals that even the most precise data carries a temporal displacement. What you see is a history, not a contemporaneous snapshot. Your understanding of events is constrained by the finite speed of light, a fundamental property that preserves causality, yet imposes observational uncertainty. Extreme astrophysical phenomena accentuate this challenge. Gamma-ray bursts, hypernovae, and neutron star mergers emit light across multiple wavelengths, each interacting differently with intervening matter. Observation demonstrates that some photons are absorbed, scattered, or delayed, producing afterglows and secondary emissions that arrive at staggered intervals. Measurement allows reconstruction of energy release and sequence of events. Yet any inference about the current state of the source is inherently indirect. Light carries both information and ambiguity, encoding structure and intensity, while simultaneously masking direct access to the present. The paradox intensifies when temporal resolution is considered. High-energy events unfold over milliseconds to minutes, yet the light you detect has traveled millions or billions of years. Observation enables measurement of photon arrival times and energy distribution, but the combination of distance and speed creates intrinsic uncertainty. Gravitational effects along the path can warp timing, altering the apparent sequence of events. Measurement is precise, reproducible, and yet fundamentally constrained. The farther the source, the more the universe itself mediates the signal, filtering and reshaping information in ways beyond direct control. Light also interacts with the expanding cosmos. Cosmological redshift stretches wavelengths, dilutes energy, and separates events in time. Observation confirms that photons arriving from the same source can encode signals from different epochs of emission. Measurement demonstrates that energy and timing are coupled. A photon's redshift reflects both velocity and distance, providing measurable insight into the universe's expansion while simultaneously complicating interpretation of the source's present condition. You confront a subtle paradox. The more distant the object, the more information is encoded in the light, yet the less direct access you have to the immediate properties of the system. Intervening matter further complicates interpretation. Gas clouds, interstellar dust, and cosmic magnetic fields scatter or deflect light, producing measurable distortions in intensity, polarization, and spectrum. Observation allows modeling of these effects, yet uncertainty remains. Measurement reconstructs both the history of the source and the characteristics of the intervening medium, but it cannot fully recover the unmediated present. The light you receive is simultaneously a record and a transformation, a measure of reality filtered through space, time, and energy. Ultimately, the limits of light travel reveal a universe where observation is always indirect, constrained, and partially ambiguous. Measurement confirms that photons are reliable messengers of the past, yet the farther they come, the more distant the reality they represent. You are confronted with the quiet unease that seeing is not knowing. Light encodes, conveys, and transforms, allowing reconstruction of history while withholding certainty about the present. Even the most extreme events, measured with high precision, are subject to these fundamental constraints. The cosmos communicates across vast distances, yet its message is always refracted, delayed, and incomplete, leaving interpretation perpetually provisional and observation inseparable from uncertainty. Quasars, beacons of energy. Supermassive black holes at galactic centers produce quasars, whose luminosity rivals entire galaxies. Observation confirms regular variability patterns over decades, yet the source processes involve physics extreme enough to distort space-time locally. Measurement forces you to confront energy scales that stretch intuition. From your perspective, luminosity is additive. Stars contribute predictable amounts, and galaxies shine according to the mass and age of their stellar populations. Quasars violate this intuition. Observation shows that a single compact object, a supermassive black hole feeding on infalling matter, can output energy equivalent to trillions of suns. Light, X-rays, and gamma rays are emitted with directional and temporal regularity, yet the processes producing them occur in regions smaller than our solar system. Measurement confirms that these extreme energy concentrations generate observable effects across entire host galaxies, influencing gas dynamics, star formation, and even the intergalactic medium. The mechanics of quasars are measurable yet counterintuitive. Accretion disks funnel matter inward, converting gravitational potential energy into radiation with near-perfect efficiency. Relativistic jets launch perpendicular to the disk, carrying matter and energy far beyond the galactic core. Observation of jet collimation and variability indicates that magnetic fields, angular momentum, and relativistic effects all interact to produce coherent, measurable emission. Measurement of periodicity and spectral shifts allows reconstruction of the disk's structure and dynamics, yet the energies involved exceed human intuition. The same processes that sustain brightness also distort space-time, bending light paths and altering timing signals detectable even across billions of light years. Quasars also illustrate extreme temporal and spatial scaling. Variability occurs over decades as the inner disk adjusts, yet light from these systems may take billions of years to reach Earth. Observation shows that brightness fluctuations are correlated across wavelengths, encoding information about inner disk turbulence, jet precession, and relativistic frame dragging. Measurement allows disentangling of these effects, revealing that even subtle changes are amplified by the system's extreme energy density. You are confronted with the paradox that a seemingly continuous light source encodes dynamic processes operating on microscopic scales relative to the galaxy, yet observable across cosmological distances. The interaction with the surrounding environment further demonstrates extremity. Radiation pressure from the quasar expels gas from the galactic core, influencing star formation and interstellar medium composition. Observation confirms that these outflows are structured, measurable, and capable of reshaping the host galaxy over millions of years. Measurement reveals that energy is neither isotropic nor smoothly dissipated. It is concentrated, directional, and coupled to both matter and magnetic fields. Even small variations in accretion or jet dynamics propagate outward, leaving signatures detectable through spectroscopy and radio imaging. Relativistic effects are pronounced. Light from near the event horizon is redshifted, lensed, and time-dilated, producing measurable distortions in both intensity and spectrum. Observation allows reconstruction of the geometry of the emitting regions. Yet these distortions emphasize that what you see is a combination of extreme energy processes and relativistic effects. Measurement demonstrates that understanding the quasar requires reconciling local physics with cosmological observation, linking subparsec dynamics to energy observable across millions of light years. Ultimately, quasars exemplify a universe capable of concentrating energy to extraordinary degrees while maintaining coherent and measurable patterns. Observation confirms that a single compact object can rival entire galaxies in output, distorting space-time and affecting its surroundings profoundly. You are confronted with the realization that scale, density, and energy interact in ways that defy intuition. The universe can amplify the consequences of gravitational collapse and accretion to extremes that are measurable, structured, and profoundly alien. Quasars are beacons not only of light, but of cosmic extremity, demonstrating that energy, matter, and space-time can interact coherently at scales and intensities that stretch understanding, leaving measurable traces across the universe for observers capable of precise measurement. Cosmic magnetism. Magnetic fields in galaxies and clusters shape the flow of matter and energy. You assume magnetism to be weak and predictable, yet mapping shows fields coherent over megaparsecs. Observation demonstrates order arising alongside chaos, implying that large-scale forces interact in ways that defy naive expectation. From your perspective, magnetism is a local phenomenon, observable in bar magnets, planetary fields, or the sun. You assume that its effects diminish over distance, constrained by material properties and the inverse square law. Yet cosmic scale measurement contradicts this intuition. Instruments detect magnetic fields that thread entire galaxies, influence the motion of interstellar gas, and guide relativistic particles over millions of light years. Observation confirms that these fields are coherent, structured, and persistent, often aligning with spiral arms, filaments, or shock fronts, while simultaneously interacting with turbulent plasma in ways that produce complex, measurable dynamics. The interaction between magnetism and charged matter is pronounced. Cosmic rays spiral along field lines, their paths dictated by large-scale magnetic structure rather than local collisions. Observation reveals that the propagation of high-energy particles is anisotropic, controlled by fields that stretch across entire clusters. Measurement demonstrates that energy and momentum can be transported coherently over enormous distances, producing observable effects that link small-scale processes to structures of unprecedented scale. You are confronted with the paradox that the universe organizes energy along invisible channels, maintaining order within turbulence. Magnetohydrodynamics governs the evolution of these fields. Gas motion amplifies, twists, and reconnects magnetic lines, producing phenomena observable in radio and X-ray wavelengths. Observation shows that shocks from supernovae, galactic winds, and jets interact with these fields, generating coherent patterns and localized turbulence simultaneously. Measurement allows precise mapping of field strength, orientation, and topology. Yet the interaction between chaotic plasma flow and persistent magnetic order remains fundamentally counterintuitive. The universe produces structure in what appears to be random motion, revealing hidden determinism in the behavior of energy across cosmic scales. Clusters of galaxies provide an extreme example. Magnetic fields link intracluster gas over millions of light years, influencing the cooling and heating of plasma, the movement of hot ions, and the trajectory of relativistic particles. Observation shows that the fields are neither uniform nor static. They evolve slowly but maintain coherence, producing measurable effects on radio halos, Faraday rotation, and X-ray emission. Measurement confirms that large-scale forces are interconnected, such that even subtle changes in one region propagate through the cluster, influencing matter and radiation in distant, seemingly unrelated areas. Time adds another layer of complexity. Fields evolve over billions of years, yet their influence persists, guiding the flow of energy and shaping cosmic structure. Observation allows reconstruction of historical dynamics. Relic fields and clusters indicate past mergers, shocks, and galactic activity. Measurement reveals that magnetism is a record of both past and ongoing processes, simultaneously storing information about history and influencing the present. You confront the realization that magnetic structure operates across scales, mediating energy and information in ways beyond direct perception. Ultimately, cosmic magnetism demonstrates that forces you consider weak and local are instead central to the organization of matter and energy on the largest scales. Observation confirms that order and chaos coexist. Magnetic fields thread galaxies, guide energetic particles, and shape plasma flows while interacting with turbulence and extreme astrophysical events. you are confronted with the quietly unsettling understanding that the universe employs invisible channels to structure energy, maintaining coherence in a system governed by both determinism and turbulence. Large-scale magnetic forces illustrate a cosmos where influence is pervasive, measurable, and subtly counterintuitive, linking distant regions through invisible, persistent networks of energy and information. The echoes of the early universe. Gravitational waves from the early cosmos are faint but measurable. They encode information about the first instance of expansion, yet interpretation is incomplete. Observation implies that even the oldest events carry signatures that subtly contradict uniformity, leaving you with a history that is partially comprehensible but deeply puzzling. From your perspective, the early universe is often pictured as homogeneous, a smooth sea of energy and matter gradually coalescing into structure. Yet instruments detecting primordial gravitational waves reveal subtle ripples, small perturbations embedded within the expansion. Measurement confirms that these ripples are coherent, encoding information about density fluctuations, energy distributions, and space-time curvature at epochs only fractions of a second after the Big Bang. Observation demonstrates that even at the earliest times, the universe was not entirely uniform. Microscopic asymmetries existed, amplified over billions of years into the structure you now perceive. The signal is weak, yet the precision of measurement allows reconstruction of the conditions that produced it. Quantum fluctuations, inflationary dynamics, and phase transitions in the primordial plasma all leave measurable imprints. Observation shows that these effects are systematic, reproducible, and embedded within the gravitational wave background. Measurement allows you to infer statistical properties of the first structures, yet the details remain elusive. The universe encodes history in space-time itself, yet the record is partial, filtered, and incomplete. Even when you measure with extraordinary precision, gaps remain, leaving reconstruction of the earliest moments necessarily probabilistic. Temporal scaling compounds the challenge. The waves you detect have traveled almost the age of the universe, stretched by cosmic expansion and altered subtly by interactions with matter and energy along the way. Observation demonstrates that light and gravitational waves from these early times are delayed, redshifted, and slightly modified by the intervening cosmos. Measurement requires disentangling original signals from these distortions, yet the result is never fully direct. You see the past clearly, yet it is mediated through layers of space, time, and energy, producing a paradoxical sense of clarity and obscurity simultaneously. Spatial variation introduces further complexity. Large-scale structure, such as filaments, voids, and proto-galaxies, interacts with the primordial waves, producing anisotropies in amplitude and orientation. Observation allows modeling of these interactions, revealing that the echoes of the early universe are not uniform across the sky. Measurement indicates that even minor deviations in density or energy distribution billions of years ago leave detectable signatures today, encoding a history that is coherent yet laced with irregularities. You are confronted with the subtle realization that early order coexists with primordial unevenness, producing measurable effects across space and time. Ultimately, the echoes of the early universe reveal a cosmos both predictable and alien. Observation confirms that gravitational waves carry structured, measurable information from the first instance of existence. Measurement allows partial reconstruction of those conditions, yet the record is incomplete, nuanced, and counterintuitive. You are confronted with the knowledge that uniformity is an approximation, that the first moments of time were marked by variations whose influence persists today. and that history itself is embedded in the very fabric of space-time. Even the oldest, faintest signals convey complexity. The universe preserves its origins, yet simultaneously obscures them, leaving you with a comprehension that is profound, precise, and quietly unsettling. The transience of power. Extreme events are fleeting. A gamma-ray burst lasts seconds. A tidal disruption event may fade in months. Yet their influence persists across space and time. Observation demonstrates that duration is decoupled from impact, a fundamental contradiction between temporal scale and energetic consequence. From your perspective, energy release is typically associated with time. A slow burn distributes its influence gradually. A brief flash produces localized and minor effects. Yet astrophysical measurement contradicts this assumption. The most energetic events in the cosmos, though transient, deposit energy into their surroundings at scales that persist long after the initial flash fades. Observation shows that these events can alter star formation in nearby regions, drive shockwaves across interstellar gas, and generate gravitational disturbances that propagate for millions of years. Measurement confirms that brevity does not imply insignificance. Impact and duration are uncoupled. Gamma-ray bursts exemplify this paradox. In seconds, they can emit more energy than the sun will produce over its 10 billion year lifetime. Observation records the initial burst and subsequent afterglow across multiple wavelengths, revealing a complex interplay of high-energy photons, magnetic fields, and relativistic jets. Measurement demonstrates that despite the event's fleeting appearance, its radiation interacts with the interstellar medium, triggering ionization, heating, and particle acceleration. The after effects persist, measurable across light years, yet the origin itself has vanished in time. You are confronted with the quiet dissonance that what is brief can be immeasurably consequential. Tidal disruption events provide a complementary illustration. When a star wanders too close to a supermassive black hole, it is torn apart in hours or days. Observation confirms that matter is accelerated, partially accreted, and partially ejected, producing emission detectable for months or years. Measurement of energy distribution, velocity, and radiation patterns reveals that the initial destruction triggers cascading interactions with surrounding gas and dust, influencing the local galactic environment long after the visible flare fades. The transient event leaves enduring structural and energetic signatures, demonstrating that temporal brevity is not predictive of scale or consequence. Even supernovae, which unfold over weeks to months, demonstrate this principle. The explosion is brief relative to cosmic timescales, yet the energy imparted drives shockwaves that shape interstellar clouds, inject heavy elements, and influence subsequent generations of star formation. Observation allows you to trace the propagation of energy and matter across space, confirming that the event's temporal span is negligible compared to the persistence of its influence. Measurement shows that extremity is embedded in consequence, not duration, creating a dissonance between the timescale of the phenomenon and the timescale of its effects. Underlying this pattern is a fundamental property of the universe. Energy, once concentrated and released, propagates through space-time in ways that can outlast its source. Gravitational waves, radiation, and energetic particles carry signatures across vast distances, encoding both the initial conditions and subsequent interactions. Observation reveals that temporal scale is not a reliable indicator of impact. Measurement allows reconstruction of cause and effect, yet the sequence is non-intuitive. Fleeting events can have persistent and disproportionate consequences. Ultimately, the transience of power demonstrates that the cosmos does not adhere to human assumptions about time, energy, or causality, observation confirms that the briefest phenomena can drive long-term transformation. That energy can concentrate and propagate with lasting effect, and that duration is an unreliable guide to consequence. You are confronted with the realization that the universe concentrates extremity in fleeting moments, encoding long-term influence in brief flashes, leaving measurable traces that ripple across space and time long after the initial source has vanished. Duration and impact are divorced, and the universe, once measured, quietly reveals that transience does not imply weakness. Measurement reveals limits. Every observation is mediated by instruments that quantify light, gravity, and particles. Yet the act of measuring imposes limits. You capture one facet of an event while ignoring others. Observation forces recognition of epistemic boundaries, that understanding is always partial, and that power exists beyond perception. From your perspective, measurement is a bridge between the universe and your comprehension. Telescopes record photons, detectors register gravitational waves, and spectrometers analyze particles. Each device produces data, a precise map of one aspect of reality. Yet observation is inherently selective. Measurement captures what is detectable within a given bandwidth, sensitivity, and temporal resolution. Instruments cannot access all phenomena simultaneously, nor can they transcend the physics that govern their operation. Observation, no matter how precise, is an act of limitation as much as revelation. Extreme cosmic events expose these boundaries. Gamma-ray bursts, neutron star mergers, and quasars emit energy across the electromagnetic spectrum and through gravitational waves, neutrinos, and cosmic rays. Instruments capture slices of this emission, each providing information that is accurate within its domain. Measurement allows reconstruction of energy release, timing, and directionality, yet no single observation conveys the totality of the event. Observation confirms that your understanding is necessarily incomplete. Facets of reality exist outside your ability to detect them simultaneously, producing epistemic gaps in even the most measured systems. Temporal constraints compound these limitations. High-energy events occur on timescales vastly shorter than the intervals over which data can be accumulated or processed. Observation captures discrete moments, yet the phenomena themselves evolve continuously, producing dynamics that are partially obscured or aliased by measurement. Measurement reveals the structure that is accessible, yet it cannot fully reconstruct the total sequence of cause and effect. You confront the quiet paradox that precision in one domain necessitates ignorance in another, that every instrument prioritizes resolution along certain axes while sacrificing clarity along others. Spatial scale introduces further complexity. Telescopes, detectors, and interferometers provide finite fields of view. Observation confirms that extreme events are not isolated but embedded within broader structures: galaxies, clusters, filaments, and voids. Measurement captures local intensity, spectra, or timing. Yet interactions with surrounding matter often remain undetectable. Even when inferred through indirect effects, these interactions highlight the partiality of observation. You are forced to recognize that reality extends beyond the measurable, that energy, structure, and causality persist in domains beyond the reach of current instruments. The act of interpretation magnifies these epistemic limits. Data requires modeling, assumptions, and extrapolation. Observation produces patterns, yet these patterns are shaped by the frameworks you impose. Measurement demonstrates consistency and reproducibility, yet it simultaneously emphasizes contingency. Understanding depends on the instruments, the chosen methods, and the resolution of analysis. you perceive order. Yet order is inseparable from the limitations of perception and the tools used to measure it. Ultimately, measurement itself is a mirror of cosmic extremity. Observation reveals energy, structure, and dynamics, yet it also exposes the boundaries of comprehension. Precision highlights ignorance. The more accurately you measure one variable, the less access you have to others. Instruments mediate reality, capturing slices of power while leaving unobserved dimensions beyond reach. You are confronted with the quiet, unavoidable realization that no measurement can fully encompass the universe's extremity. Power exists independently of perception. Understanding is always provisional. The cosmos is knowable, measurable, and yet perpetually beyond total apprehension and observation, for all its rigor, only confirms the existence of what remains unseen, unmeasured, and fundamentally unknowable. The universe is in different extremes. Ultimately, the cosmos is neither benevolent nor hostile. It produces extremes with precise predictability, yet their scale and consequences are detached from any concern for observers. Observation reveals that the most powerful events in space are indifferent, measured, and unavoidable, leaving you to confront their magnitude without recourse. From your perspective, nature is often interpreted through human experience. Dangers can be avoided, resources are exploitable, patterns can be used to anticipate outcomes. Yet in the cosmic context, this perspective fails. Gamma-ray bursts emit energy across billions of light-years with no regard for planetary systems. Supernovae inject matter and shockwaves into their surroundings, shaping future star formation without foresight or purpose. Measurement confirms that these phenomena obey physical laws precisely, yet they do so independently of observers, carrying consequences that cannot be mitigated, anticipated, or altered. Observation underscores that extremity is intrinsic, not instrumental. Scale magnifies the indifference. Colliding black holes, neutron star mergers, and hypernovae release energy incomprehensible on human terms. Observation allows measurement of gravitational waves, electromagnetic emission, and particle acceleration, yet the systems themselves remain unaffected by human perception. Measurement confirms that their evolution is governed by mass, energy, and space-time curvature, not intention or consequence. You are confronted with the quiet realization that extremity exists as a property of the cosmos itself, independent of relevance to life, awareness, or comprehension. The universe produces power because the laws of physics demand it, not because there is need for its expression. Temporal scale reinforces this detachment. Many extreme events unfold over seconds, months, or millennia, yet their effects persist across cosmic history. Observation shows that a gamma-ray burst that occurred billions of years ago may still influence the interstellar medium, shaping star formation in a galaxy you observe today. Measurement indicates that duration is irrelevant to consequence. Brief events can produce long-term structural and energetic effects without feedback, intention, or moderation. You confront the dissonance that the universe's most profound activity operates on its own timescale, entirely indifferent to any sense of human chronology. Even predictability is devoid of concern. Physics allows modeling of black hole mergers, supernova energetics, and relativistic jet formation with high precision. Observation confirms reproducibility of patterns, regularity of physical processes, and predictability of energy output. Yet this predictability is neutral. Measurement allows you to anticipate consequences in theory, yet does nothing to mitigate their detachment from experience. The cosmos operates according to law, not empathy. Extremity is inevitable because the structure of matter, energy, and space-time compels it, not because it fulfills any narrative. Ultimately, indifference is inseparable from power. Observation confirms that the universe produces extremes that are measurable, reproducible, and unavoidable. Measurement demonstrates that consequences propagate without regard for observers, environments, or outcomes beyond the local event. You are confronted with the unsettling realization that cosmic extremity exists independently of concern, that energy, mass, and space-time evolve according to deterministic patterns, and that observation reveals magnitude without recourse. Extremity is embedded in the fabric of reality itself, and its unfolding is neither guided nor tempered by any principle other than physical law. The universe's indifferent extremes leave you with a profound tension. Knowledge allows measurement and understanding, yet awareness does not confer influence. Observation exposes precision without purpose, consequence without intent, and power without moral dimension. You are left to perceive magnitude, trace energy, and comprehend structure, yet all of it exists without reference to observers. The cosmos manifests its extremes, and in doing so, forces recognition of its autonomy, detachment, and quiet, measured indifference, a reality that is both knowable and fundamentally unconcerned with your presence.